you, Dan, and thank you, everyone, for being here. So just a reminder, we're going to have the talk and then each talk. And then after each talk, there's going to be 2 minutes for question and answers. So just submit your questions in the app. So our first speaker is Bruno Hebling Vieira, and he's going to be talking about decomposing the evaluation of probabilistic prediction of future cognitive decline in aging.
Thank you, Julia, and thank you, Dan. Welcome, everyone. Good morning. I have to check how to do this. I have no disclosures. The background and motivation for this talk is that we know that cortical and atrophy differences in aging and also in Alzheimer's or neurodegenerative diseases, they usually precede cognitive decline. You see that in memory, you see that in other cognitive aspects. So we know that we could, or we hope that we could use these differences in cortical morphometry and brain morphometry in general to predict future cognitive impairment in people. So as an example, if we have someone from ADNI here, for example, we have a participant and we have their true cognitive impairment level. This is the CDR, clinical dementia rating, sum of boxes. Goes from 0, no impairment, to 18, complete impairment, basically. And here's the time since this scan. So we know that this person is at 5, which is already close to moderate dementia. And we could build a model that this is their true CDR 5 years into the future. We could build a machine learning model that predicts CDR into this time span, 5 years into the future. But at the same time, we know that this participant has more data. They have multiple sessions for CDR. So we can also include time as one of the features, and then you get a continuous time model. So you can predict their cognitive impairment in the future longitudinally based on this image in the present. The problem with this thing is that it's a point estimate only. So you can see that the line is not really tracking anymore the truth for the subject after 6 or 7 years into the future. But because you have only a point estimate, you cannot really have certainty about your predictions. We would like to move from this to this, which is a probabilistic model where you can infer uncertainty around your estimates. And you can see here that this is the confidence interval, that it does track well with the truth, but it does veer off very far into the future, and that's okay. And we do that with a classification model. And remember that the same subject actually has many images. So you can see here that this person is showing some hallmarks of cortical and brain atrophy, for example, ventricular enlargement. And then using the same model, we can go and predict the future impairment, cognitive impairment. So you can see that the gray area here is the past, and the past is moving forward because these images, they are further as the person ages. The problem with this is that evaluating probabilistic predictions is not as straightforward as evaluating point estimates. So what we do is that we evaluate then in this scale, which is a ranked scale. So we evaluate, instead of evaluating the probability of having CDR SOB equal to 4, such as this example, we go and evaluate this ranked probability, which is the probability of having CDR SOB equal or less than 4 versus having more than 4. And to evaluate probabilities, we use the Breyer score, which is a proper scoring rule. So it's going to be minimized when you have the true expectation. And it's basically these yellow areas here squared per subject, and then you average per CDR SOB level across subjects. All right, so the Breyer score is a proper metric, but it does 2 things at the same time. So if you had a plot like this is called the reliability diagram. You put the predictions in the x-axis and the truth, it's a binary target, in the y-axis. And if you go and take the expectation of the truth given the predictions, you get this aspect here, this line. And if the line is close to the diagonal, you get predictions that are calibrated, or you can call them reliable predictions. So you can show mathematically that the Breyer score has these three components. One is reliability. It's these red lines that you see here showing now. And it basically tells you how close are your predictions to the true occurrence of the event. So if you say 50% chance, does it really occur 50% of the time? The second line here, the orange, or I guess yellow in the screen line, is resolution, which is, you can see that they are separating pushing the points from the base rate. It's how much do the predictions separate the classes. And this one should be maximized. And there's a third component, which is just the variance, and you cannot see that from the reliability diagram, but that's constant across models. If you have multiple models, apply to the same data set. And then as you move the predictions around, you can see that the reliability and the resolution on the bottom, they change. So some will be very reliable, and some will be not resolved, and some will be maybe completely wrong, but that's something you can quantify. And then if you have perfect predictions, you get zero reliability, maximum resolution. That's the perfect Breyer score at 0. If you were to predict the base rate, surprisingly, you would say that this is a bad prediction. But you have perfect reliability again because you say it's happening 50% of the time, and it actually does happen 50% of the time. The problem is that this prediction has no resolution. It does not separate the classes. And further, you could have the worst Breyer score possible. When you have a positive case, you say 0% chance. When you have a negative case, you say 100% of probability. And this prediction, it actually has the maximum resolution, but it has no reliability at all. It's completely wrong. One thing about this is that reliability is something that you can solve post hoc. You can just recalibrate, for example. But resolution, not really. So for our model, we took data from ADNI for training. We took free surface derivatives, the usual ones, that's cortical morphometrics, cortical thickness and surface area of these regions from the Destrier atlas, and also some other volumetric features, very common ones like ventricular volume and hippocampal volume and other things. Important covariates, including risk factors for Alzheimer's, such as the APOE genotype, age, sex, and education. And we also take into account the present CDR scores, because we need to take into account that some people are not cognitively unimpaired at the baseline. All right, so for results, as I said before, these are comparisons, they are ranked. So we're comparing people that have CDR equal to 0 versus having CDR bigger than 0. And the main metric is the Breyer score. So you see that with time, the Breyer score increases, which is bad. It means that the predictions are harder into the future. There's also a problem with, well, we have less data into the future, so that also comes into account here. But when we have our decomposition, you see here that the reliability is low, which is good, which means that our predicted probabilities are close to the true occurrence. And resolution is also low, which is bad. That means that even though we are doing a good job at predicting, estimating the probabilities, they do not really separate the classes. And then we can go and remove MRI, for example, from a model, and then we have this blue line here. And the dots, they show significant differences from the full model. And when we remove even CDR and you do something that's very common in clinical trials, you get the yellow line, which just has the covariates. So we can, if you just look in the Breyer score, you're gonna find that there's this area where MRI improves the performance. But if you just had that, you wouldn't be able to say why is that the case. When you do decompose, you find that MRI only improves reliability. It's not really separating the classes any further, and so you can say that for this specific scenario, you only get better probability, not more cluster probability. If we move a notch up, now 0 or 0.5 versus bigger or equal to 1, now you only have these three significant differences, and we can see that actually, or at least assign a meaning for this one, that this one is different because of reliability. So MRI is improving reliability in this area, and these other two, it's due to improvements in resolution. So the takeaway here is that the prediction of future CDR SOB is highly reliable. MRI is more important for lower impairment levels, and for high impairment levels, it's more important only in longer time windows. And something that we show in our poster, you are welcome to find me at 157. The decomposition, it shows that external data sets, the generalizability to external data sets comes from improvements in reliability. We are looking for collaborations to extend this framework to other scenarios, so please reach out if you have a scenario in mind. And with that, I would like to thank you all, and thank you my collaborators, data providers, Edney and Oasis. We have results on Oasis in my poster, and also funding received for this research. Thank you.
Thank you, Bruno. That was a fascinating talk. We have a question. The question is, it could be more important when the SOB score goes from slow and steady to rapid and increase. And so the question is, can any model predict that?
Well, I think our model does not do that. I can tell you that. I do think, it's definitely important. We could move to, because if you look into our model, it's a cross-sectional to longitudinal model, so you take a data point in the present and try to estimate everything in the future. I think a longitudinal model could be better, a model that incorporates more data points, more imaging samples, and you could also have something that's called functional prediction. So instead of predicting every single point, every single time, you predict a trajectory directly, and then you do a sampling of these predicted trajectories. And yes, I definitely agree. I think it's something that's important, and our model does not do that right now, at least. So if you, I don't know who you are, but if you are doing that, please come and talk to me.
Okay, and one last question that I have is, so you showed us your models with MRI, and we know that there's other techniques that are widely used in aging research, such as PET. So how would your models behave if you were to include PET instead of fMRI or MRI?
I think PET, amyloid PET or tau PET would be very important, because we have people that that go and show Alzheimer's symptoms in the future. So I assume that they would improve the models. What I really think is that they would improve maybe one of the aspects and not the other. Maybe we would get more resolution, so cluster probability. And it's because we still have very good reliability from our models, but that's something that we are investigating, and I think it's a very good idea.
Thank you.